All right. This is Jun from ZJNU University in China. Today I will present one recent research from my lab. The title is Theta band behavioral fluctuation synchronized interpersonally during cooperation. Well, by looking at today's meeting agenda, I found most talk is talking about hyperscanning by using various neural imaging methods like the EEG, like the fMRI, like the functionaries. So I'm afraid my talk will be a little bit disappointed because I'm not going to talk about any fancy neural image method today. I'm talking about the behavioral fluctuation. So I hope everyone can hang in there and stick to the end of my talk. Okay, so human behavior fluctuates over time, but this fluctuation was usually regarded as management noise. Let's see one classical personal queuing task. So I think everyone familiarized with this task. We start with a queue to indicate participants to pay attention to left or right. And after randomized SOA, a target will be presented. People need to make a response to target. So in this paradigm, what we mainly interest is the mean of the reaction time. And actually, people's reaction time can be varied trial by trial, but we only interest as the standard deviation of the reaction time. But what I want to say is these fluctuations actually include rhythmic information, and this information could resemble neural oscillations. So in the real experiments, how can we detect and extract this rhythmic information? Let's see that's a demonstration. So firstly, we'll give a salient stimulus to phase resetting the neural oscillations. Anything can be used as a salient stimuli, like the flash, like the audio. So after phase resetting, we'll present target stimuli as the difference SOA. And this SOA can be dense sampling. Usually it will include like 40 or 50 SOAs. When the target stimuli is presented as the peak of the oscillations, the behavior performance will be boosted. But on the contrary, if the target stimuli is presented as trough of the oscillations, the performance will be a little bit weakened. So by doing this way, the behavior performance will be fluctuated depends on what's the timing point the stimuli was presented. And this way, the fluctuation can be used to like the mimic or resemble the neural oscillations. Let's start with examples. This was like the one classical research in the behavioral oscillations, which was published in 2012. It's also a classical personal paradigm. After a flash event, the target event will be presented. Participants need to make the response to the target event. And we can see right here, the SOA between flash and targets are varied from minus 600 milliseconds to 1 second. And we can see no matter the target stimuli is on the same side or opposite side of the flash event, the behavior performance is fluctuated. You can see it's upside, and upside. By applying the Fourier transformation, we can see there's a special peak around theta band hertz, which is like the 4 hertz right here. So the same and opposite side also showing the theta band spectral peak. And the phase angle between these two conditions are anti-phased. You can see from this polar space. So what this study telling us is we can detects and extracts the rhythm information from the human behavioral fluctuation. But so far, almost all the behavioral oscillation study focus on the perceptual field, like the vision, like the audio. So the question we want to ask is, what's the behavioral oscillations in the more complex social interaction behavior? Like this video says, the rolling boat, what's happened in these situations? So before I answer the question, I want to talk about some great and exciting research on the interbrain synchroning during corporations by using either the functionaries or functional EEG or some other measurements. So this example is by using the functionaries, which using the very simple joint action task. So you can see this result. This is like functionaries result. People showing the highest interbrain synchrony during cooperation task compared to competition, compare single one task. Similarly, the interbrain synchrony by using the hyposcaling EEG also showing the higher theta band coherence. Also, studies showing this interbrain synchrony can be impacted by gender, which you can see the male-to-male pairs has the strongest interbrain synchrony. But I hate to say that the female-to-female pairs show the lowest interbrain synchrony. Also, the leader-follower relationship can have the significant impacts on the interbrain synchrony, which you can tell from left to right. The leader-follower's relationship has the strongest or stronger interbrain synchrony compared to follower-to-follower. So we can tell the gender, the leader-follower relationship, both has a significant impacts on the interbrain synchrony we measure. So let's back to our question. We want to ask in our study, in cooperation, does the behaviors fluctuated, synchronized between co-actors? So in other words, can we find a similar behavior to behavior synchronization to resemble or to mimic the brain to brain synchronization? So that's the key question we want to address in this research. All right. So we use a very simple and classic joint action task. You can see right here, two persons sitting in the front of computer and make a response to green targets on the screen. Actually, this is one of my students, and this is another my student. So during the task, we firstly will present a white circling to indicate the ready, to let people know, let participants know they are ready to make a response. Then after a various SOA, which is like from 200 milliseconds to 1 second in steps of the 20 milliseconds, a green target will be presented on screen, and the people need to respond to the target stimuli depend on different conditions. In the cooperation conditions, the participants need to reduce their reaction time difference as small as possible. But in the competition conditions, they need to respond to the green target as fast as they are possible so they can beat their partners. After their responses, the screen will show the corresponding feedbacks. For example, whether they win or lose in last trials and how many scores they have accumulated so far. So that is like kind of like experiment procedures. So what's our hypothesis? Our hypothesis is after we give the ready signals, these ready signals supposed to reset the phase of the oscillations. You can see right here, there are two oscillations. One is the solid blue line, the other is the dashed blue lines. They represent oscillation for the two persons in this task. The blue color represents cooperation task. The red color represents the competition task. So our hypothesis is after ready signal in cooperation task, the phase difference between these two persons, the phase difference between these two persons will remain relative constants. So you can see the difference between the dashed line and this solid line is relative constant across time. But on the other hand, the phase difference between the solid line and dashed line in the competition conditions is a little bit jittery. They are not constant. So that's our hypothesis. We think by using the phase coherence, we can pick up the difference across condition and across tasks. So let's see the result. So this is like the time series or the reaction time. The left is cooperation, the right is competitions. So we can see the reaction time actually is like fluctuate across time from 200 to 1000 SOA. Similarly, the same fluctuation we can see in the competition task. But how can we compare these two conditions? We need to extract the rhythm information from these two time series. So how can we do that? Let's see our analyze procedure. So you can see at the beginning, we got the two time series for the cooperation and for competition. Then we do the normalization and the trend for this original time series. So at first beginning, we apply the Fourier transformation like the other previous research to get the amplitude spectrum. So that's exactly what people did in the before. But our new analyze, how can we compute the interpersonal coherence? I see the example here. This is like 5 Hertz phase coherence, the phase time series. You can see one is a solid blue lines, the other is like the dashed blue lines. These are the phase time series for two persons. And can you see this like the black dashed line? This black dashed line represents the phase difference between these phase two time series. So after that, we plot each phase difference in this polar space. You can see that each blue lines represents each phase difference right here. So in this way, we can get the distribution of the phase difference in the polar space. Then we're going to calculate the mean vectors of these phase different distributions. And the length of the mean vectors can be used to quantify the interpersonal phase difference. So you can see the more clustered this distribution, the larger the interpersonal coherence, the more disputed these phase distributions, and the smaller this length of the vectors. So that's the measurements we use to quantify interpersonal phase coherence. So let's see the result. At the individual level, we are interested in the amplitude spectrum. Here, we use the permutation test with FDR corrections. So everyone can see these dashed lines. So that's the line represents the thresholding line. So anything beyond or above this line can be treated as significant. So from this plot, we can see in cooperation and in competition, there's nothing significant. Everything is below this like dashed line. But when we compare these two conditions together, we found some frequency showing the significant condition difference, which represented in this black dot right here. So this is like the individual level amplitude difference. So let's see what's happened to the phase coherence at the group level. Right here, you can see there's something here, right? There's something here in the cooperation, which is the theta band and the alpha band. What that means? So that means in the cooperation condition, the theta and the alpha phase coherence are relatively significant right here. But there's nothing here. There's nothing here in the competition conditions. When we compare these two, the theta phase difference, the theta phase coherence, show the significance like the condition difference right here. So this result telling us like when compare the cooperation and the competition, the theta band phase coherence showing a significant group difference, the condition difference. So the next question we are very interested is, what's the leader-follower relationship in cooperation? How are we going to quantify this relationship? If we can quantify this relationship, what's they related to other measurements, like the scores, like the phase coherence we just calculated? So let's see how we're going to quantify the leader-follower relationship here. So we use a balance index to quantify the leader-follower relationship. So what's the balance index? It's very simple. We use the count of the trial, the follower leading in the trials, divided by the count of trial, the leader leading will respond faster in that trial. To make this balance index easily to understandable, we put the two demonstration scenario. So in the first scenario, we can tell the one person leading all the time in all the trials, almost in all the trials. What that means? That means almost in every trial, this person always making faster response compared to his partner. So you can see here, they're almost all the blue color. Blue color represents leader, and the red color represents follower. So from this graph, you can see they almost all the blue color. So that means the leader leading all the time. So correspondingly, right here, the balance index is very small. It's approaching to 0. It's 0.0018. It's very, very small. So that's one extreme scenarios. Let's see the other scenarios. Let's say two persons has an equal count of the leading. So which we can understand in 50% of trial, one person leading will respond faster. In another 50% trial, his partner leading will making faster response. So we can see right here, the blue color and the red color, they have almost the same equal account. So right here, the balance index equal to 0.995 is very, very approaching to 1. So when balance index is approaching 1, we can tell let's now clear leader-follower distinction. So two people, they just make a response, like 10 by 10. In this time, I'm faster. In next time, you are faster. So that's the balance index we pick up to quantify the leader-follower relationship. So the next step, we want to say, okay, we got the balance index. What's the relationship between this balance index and other measurement we calculated? So let's see the correlation result. So the first correlation we checked is between balance index and the final score. So we can tell when the balance index getting smaller, the final score is getting higher. So remember the definition we put on balance index. The smaller balance index, which means these two persons has a very clear leader-follower relationship, right? We just mentioned. So what this correlation tell us? It's telling us when there's more clear leader-follower relationship, the score will be higher. Okay, let's see the other correlation. So we can see the similar relationship between the balance index and theta band coherence. Okay, so that's telling the same story. When there's the more clear leader-follower relationship, the theta band coherence is higher. So which means the theta band coherence has some behavioral relevance. When the leader-follower relationship is getting much more clear, the theta band coherence is getting higher. Let's see the last correlation. So you can see right here, although there's no significant correlation, but there's a trend. The trend telling us when the theta band coherence is getting higher, the final score is getting higher. So the theta band has another behavioral relevance. Okay, so what have presented so far, all the results are based on the male-to-male pairs, right? But I think everyone can still remember I mentioned gender impacts on the interpersonal coherence, right? So we try to test these effects on our behavioral results also. So we pick up another 20 pair, like the same way, the time course. The left is cooperation, the right is competition, and we did same analyze as the male-to-male pairs. But we didn't find any significant coherent result, either on the single cooperation or competition results, or the difference, the comparison between these two conditions. So what that means? That means in the female-to-female pairs, we didn't observe the significant theta band coherence as we observe in the male-to-male pairs. So this is kind of like similar to what we presented. So what's happening in the interbrain, like the functional synchrony. So they also reported the highest interpersonal brain synchrony is in the male-to-male pairs. The lowest is in the female-to-female pairs. So our results is kind of consistent with the previous interpersonal brain synchrony. So let's take a break. So the summary actually is very simple. The first one is cooperative behavior fluctuates, but not reasonably enough at individual level. Remember, we didn't find any significant amplitude spectrum result, right? We didn't find. But on the contrary, at the group level, for male-to-male pairs, we found there's a significant theta band in the personal coherence. This theta band actually is consistent with previously EEG hyperscanning results. They both reported like the theta band hyperscanning result. Secondly, the theta band interpersonal coherence correlates with the behavior measurement, especially with the leader-follower relationship. So what that means? That means the theta band interpersonal coherence we just reported has some behavior relevance. They can be used to predict some behavior measurements, like the relationship, like the scores. So maybe in the future, we can just use the simple behavioral paradigm to do the same thing as we did in the previous, like the hyperscanning mirror image method. We can get a similar result, but maybe the behavior management is much lower cost. We don't need any fancy machines. We just put people in the lab and put them to do some simple behavioral task, and we can get a similar result. Well, so no such results for female to female pairs. So what to do next? Right now, we are trying to pairing the female with leader trait with the female with the follower trait. So probably we're going to recruit the female participants, and we will let them to do some like questionnaire to identify which one with the leader trait, which one with the follower trait. Then we'll pair these two kind of like the female participants together to form a leader-follower structures. We hope by doing this way, we can boost their cooperation performance and increase their theta band behavioral coherence. So that's what we're going to do in the next. All right. So that's all for today's talk. It is pretty simple and straightforward. So I would like to take the final minute to thank all the group members in my lab. And I'm not sure everyone can tell we have more female students compared to male students. I think that's a specialty of our normal universities. But we're trying to make change. We're going to recruit more and more male students in my lab. Okay? Right? So I think that's the end. Thanks, guys, for your attention. So anyone has a question?
Hi, Jun. I have a question. Can you hear me?
Yeah, go ahead.
And there is also someone who put a question in the chat before me.
I didn't notice that. Actually, my screen is kind of full screen. I couldn't see any chat window.
I can read the chat question first since it was there. So which method do you choose to normalize the reaction times and why? It seems not the z-scores.
Hold on. Let me bring, how can I bring up to my chat window? Oh. Okay, I think you were asking the method section, right? The normalization.
This wasn't my question though, but it was about how to normalize the reaction times.
Well, I mean, the purpose to normalize the trend is usually you can tell when the SOA getting bigger, the people has more time to like the preparing for the target. So you can see the time series right here. You can see right here. So this sort of linear trend. When the SOA getting larger, the rest time getting smaller. So that's kind of linear trend we want to remove. So we want to remove this linear trend to get this like the normalized fluctuated time series.
Mm-hmm. Okay, and do I have time for my question as well?
Yeah, go ahead.
Yeah, I thought it was really interesting that you take a frequency band, for example, that we have evidence for synchrony and neurophysiological data, and say, do we also see this in behavioral data? And I also have been working a bit in the area of multi-frequency synchronization, but actually for movement data of team problem solving. And I'm curious if you think this type of approach would also apply to movement data as well.
Well, I mean, actually, in the paper we published in the introduction part, we specialized to introduce the previous research on the movement data, like the ball jolting, like the rocking chairs. They're quite a base, like the movements research already published. But the pattern we observe is the frequency analyze this kind of research reported is mainly focused on the lower frequency, usually around like 1 hertz.
Mm-hmm.
So like you rocking your chair, I mean, you can't like rocking as fast as like the brain frequency, right? It's usually like low frequency around like 1 hertz, right? So I think like that's like a different kind of like synchrony, focus on the lower frequency like movement things, and like as we said in our introduction parts, these are very important aspects by using the movement data, the movement synchrony. But the story I'm talking about today is kind of different story. So we are trying to looking for the behavioral synchrony, which has the same frequency band as the brain synchrony, which is usually around like 20 hertz from like the 0 to 20 hertz. Mm-hmm. The highest is 20 hertz. So I think that's kind of different things, but I truly believe they reflect the both important aspects in the movement, in the behavioral synchrony. They're both important. Yeah.
Your paper, is this the one in Psychonomic Bulletin you mentioned?
Yeah.
Okay.
It just recently published in 2020 February. Yeah.
Thanks. I'll give it a read.
Yeah. Thanks. So I'm not sure what I